Welcome to Snap Education Step 2 of the execution phase. Just to get back in mind the entire Snap flow, Snap is a 3-steps process. We have seen in Step 1 how to adapt the application and the function so that the function could be used in an FPGA and manage additional external resources. Let's now see this Step 2. As you may have understood, we are now going to create the action that will be executed in the FPGA. The algorithm that you have coded in the software action will be, or can be, the same than the one you put in the hardware action. Just for this example, we have decided to differentiate the algorithm coded in software and hardware so that you can better identify who is doing what. As for the first step, we will use the same phases, understand what are the changes to apply. We will then look to the hardware action code and understand the structure of the file, and then we will execute this action on a CPU using a simulator tool and a model so that we can test that as if it was on real hardware. The first change that we are going to do is to create a new file for the action code that will be executed by the FPGA. This file will be located in the HLS Hello World/hardware directory. It will be very similar to the software action, but will implement an uppercase algorithm, so we will call it action uppercase.cpp. The CPP extension is for C++ and is needed for the Vivado HLS compiler. It gives more flexibility for the compilation.
Why CPP instead of C? This is important. We are going to use the Vivado HLS tool. It works with both, but it works much better with the CPP because it has more features with that. So behind that, it's always C code, but having the CPP extension is helpful for the tool. And that's only for the tool.
The second change is to add a function which reads the register where all data provided by the application are. In this example, the text-to-process has been put in server memory by the application, which has allocated some memory for that. With this memory address given by the application to the action will directly read from the server's memory the text-to-process. You will notice that the action request, read and write, and Snap execute these requests. No need to involve the CPU, no need either to understand the complex protocol and logic beneath to get this data. Snap's work is to hide that under the cover so that life remains easy for the software coder. Same for writing results. In this example, we are writing back to the server memory, but we could also have written these data in any resources handled by the FPGA, such as the card DDR, the card flash, or the card external Ethernet I/O. One thing important, addresses need to be adapted to a 64-byte address, which is the size of the data, read and written. Last but not least, the third change is to add an HLS action function on top of the process action function in which the action code is written. We have now two functions in this hardware action file. We will detail this HLS function in a minute when looking closer to the code. Let's now look to the code and discover how are structured the different boxes. Let's first go to Snap Actions Hello World HW directory. You will find one file, CPP file, which is the action uppercase CPP. Let's go into it. We look to the process action function, and we see that the first operation which is done is to get the pointers to the address in host memory where the text-to-process is stored and where we will need to write the text modified. We need to shift these addresses so that they are aligned on the 64-byte bus size. We then get the size of the text-to-process, and in the main loop we are going to see the limitation of the size of the read to a single word for this example, the read to the input address directly in host memory address, a typecast to get 64 characters from the 64-byte word, and the uppercase algorithm as the one we saw in the software action, the typecast to get back a 64-byte word, which is written directly to the host memory at the address allocated by the application. This loop is done until the text is entirely processed, and we then set the return code to success if this is the case. We could have done a read of the whole text in a single burst read, but this was more to show how things are done with a simple example. In this action uppercase.cpp, let's look to the HLS Action function. So, this function is a generic function which shouldn't be modified too much, but just updated depending on what external resource you want to access. First of all, the name HLS Action is generic for all actions coded in C and compiled with the HLS tool and shouldn't be changed. This function first contains all the ports definition. We have coded 3 different ports that will be used by the action: DIN and DOUT to read and write to the server memory, and then a commented one, which is DDR, to read and write to the card DDR. We can add the flash or Ethernet resource if we have some. We can also remove or comment them as here. In this example, we have intentionally commented the DDR port since we are not using it. This is important since Snap will remove all the unnecessary logic, so unsafe place in the FPGA. However, if you want to change that, you will need to specify in the configurator that you want to use this DDR, and so that connections are set correctly to the DDR logic. If we go a bit lower below in the code, you will see the different register mapping, action config register, which defines the ID information of the action. This ID will be read during the discovery phase that we will detail in the next bullet. We have also the ActReg registers, in which is defined the structure used to exchange information with the application. It finally contains the answer to what we call the discovery phase. Let me explain a bit more what is this phase. The server can have multiple FPGA cards and each card multiple actions. To be able to use these actions, the Snap Job Manager needs to know the inventory of all the available actions in the server. This discovery phase, done once before working any action, will read all action IDs from all cards in the server. This phase is mandatory and is initiated by a command which is snap main, that we will see later. On the action side, as soon as the action is awakened with the control flag set to 0, it has to answer its ID and exit. Otherwise, we just call the process action. Now, let's just compile our action code using a simple make. So we go to action, hello world, HW. We just do a make. This will compile only the hardware action code, not the whole design. We use here Xilinx Vivado HLS tool to convert C or C++ to VHDL. But we could use any other HLS tool. We choose this one since it seems to be the easiest one to use. Even more, it gives good results. HLS compilation must be done every time one of the action source code is modified. This will not be done by the snap process except for the first time. Look tightly to the HLS messages that are displayed. They will be key to understand any HLS compilation issue, but also all optimization information. Snap has added 2 scripts for this compilation to do basics checking. Highlight any critical timing issue that can be reported by HLS, and this needs to be solved before going further, if any. And the second script is to check if the MMIO or register mapping is done correctly. An error will be reported if user has defined registers taking more than 108 bytes in the structure. So now we have a hardware code created and compiled alone, meaning without the whole design. Now let's integrate it in the whole design so it can talk to the different resources and be managed by the job manager. We will need to set the environment if not done yet, then build the simulation model so that we can test the hardware action as if it was executed on a FPGA and discussing with the real power rate. And finally, run the application with the hardware action. If this has not been done yet, we need to set up the Snap environment. From the Snap directory, you can clean your environment to a new one by typing make clean config. This will just clean all the subdirectories. Then type make snap config. This will set up all the different variables depending on the resources we need to use. Select the alpha data KU3 card and then the HLS Hello World action for this example. Keep the XSIM simulator, which is the Xilinx Vivado simulator used as default, and select the cloud build option, which is mandatory to build and then execute the images on Nimbix FPGA card. Then just exit and answer yes to save your selection. If Snap configuration is done correctly, you will see it if all variables are set OK in the snap env.sh displayed on the screen. If some warning errors are displayed, it is recommended to correct them before going further. Now that the Snap environment has been set correctly, let's build the model of the code so that it can be run with the simulator. From the Snap directory, type the make model command. This will create the framework with all the settings that you have defined when doing the make snap config. Then gather all the snap modules useful to connect our action to the power rate server. Assign the different FPGA physical memory resources needed to implement our logic. And then compile all the different software modules we need, such as the PSLSE, which is the PSL simulation engine. Then compile software application and build the simulation model. This takes a minute or so. If the model is built successfully, you get a done on the last line. It may be good to just highlight what we are simulating. Your action code is in the circular on the right, and we need to simulate its execution with the application which is executed in the CPU on the left. As at this level we don't have the FPGA nor a power rate, we have built a model that will replace the hardware CAPI components. For simulation, all the basic hardware CAPI components are replaced by a PSL simulation engine. Therefore, the application will be able to execute the hardware action as if it was through a real power rate and with a real FPGA. Simulation is accurate enough to be able to reproduce all the problems found on real hardware, and this is really good for debug. Now that the model is built, let's run our program on it. In hardware/sim directory, type run sim to call the simulator. This will start the simulator and open a new window. Now, remember that the first thing we do is to run the snap main program to discover the action in the simulated code. Here we see that the IBM HLS Hello World action has been selected and modelized. Now let's create a file with a mix of upper and lower case characters if this file doesn't exist yet. Now let's run the program. This returns the success status, and we can have a look now to the different results. That's the original file, and that's the result. Everything is in capital letters, which means that the conversion was done successfully. Do not pay attention to the time reported. This is a time counting the time of the simulator. You can also try to switch back to execute the software action by typing the same command with the snap config equals CPU in front of it. The result will be a file with only lowercase characters. You can also use the snap_trace equal 0xf command to see more about the exchange between application and the action. Well, second step is now completed. We have ported the action from software to hardware and compiled and executed together. In the third step, we will execute the hardware action on real hardware. Let's summarize. We know that the code generated for the FPGA runs functionally OK on CPU. Once the environment set, we have used one make command to compile the hardware action from the hardware directory. We could also have used the make actions command run from the snaproot directory. To generate the model, we used just one make model to compile the whole design for the simulator. We have now in 3 different directories the 4 files useful to validate the software and the hardware action with the application.